Human beings are designed on an intermediate scale when viewed within the gigantic scope of the universe in which we live. We are hardly able to fathom the great distances of the cosmos. We are so small, and they are so vast. At the same time, we are too big to enter into the peculiar world of the microcosmos. But we have learned that everything in the universe behaves according to the rules of interaction between elemental particles, the same universal building blocks that came into being with the Big Bang. The day we were able to fully describe those building blocks will be the day we discover the reason for everything, maybe even the reason for human existence. On December 29, 1959, the eminent physicist Richard Phillips Feynman, who would be awarded the Nobel Prize 6 years later, presented his ideas at a physics conference at Caltech. The principles of physics, as I understand them, do not deny the possibility of manipulating things atom by atom. Problems in chemistry and biology could be avoided if we were able to develop the means to see what we were doing, and to make things at an atomic level. Progress that I do not think can be delayed any longer. Manipulating matter atom by atom, making things at an atomic level. As fate would have it, this spectacular proposition failed to cause much of a stir among Feynman's learned audience. But of course, he may have been the only one present who could foresee that his prediction would one day constitute a veritable scientific revolution. This is the IBM Research Center in Almaden, California. Here is where Dr. Don Eigler, a physicist specializing in atomic scale structures, works. He is possibly the world's foremost authority in this field.
So what we're going to do now is we're imaging an area of the surface with a scanning tunneling microscope. And this is just 12 nanometers across, left to right. This is a surface of the material copper. And on top of it we have some carbon monoxide molecules. Each one of these dips is an individual carbon monoxide molecule. This is where the copper crystal goes up one layer of atoms. It goes up, we call it a step.
Eigler was the first to show the world that Feynman's ideas were not so far from reality. In 1989, he proved his point by manipulating just 35 xenon atoms to draw a company's logo on a metal surface.
The way we move atoms is with really a very remarkable instrument that we have in our laboratory. It's called a scanning tunneling microscope. Sometimes people just call it an STM. This is an instrument which uses a metal needle, very sharp metal point, to image a surface. What we learned was how to use this same metal needle not only to image a surface, but to move individual atoms. We just bring the end of the needle so close to the atoms that we want to move that it can pull on the individual atoms, and we pull the individual atoms to where we want them to go along the surface. By doing this in a repeated and in a very controlled way, we can build structures at the atomic scale with atomic scale precision.
To manipulate things atom by atom, to make things at an atomic level, Feynman was right. There were no physical impediments to it. The problem is size. We're too large to move atoms as if they were chess pieces. But we've begun to develop systems that may offset this handicap. For the first time, we are able to get in direct touch with the essence of existence, something that for 25 centuries we could only imagine. We are part of a much larger, diverse environment made up of matter. Our reality is made up of living things and inert things, of liquid bodies, solid bodies, of objects with different colors and textures. However, everything that exists seems to act according to the same laws. Objects fall to the ground because of the force of gravity. Solids turn to liquids when heated, and liquids to gases. How can things of such different natures act alike? What does all matter have in common? The matter that surrounds us, the matter of which we are made. From the very beginning of our existence, mankind has asked questions about the physical essence of the natural world. In ancient Greece, Thales of Miletus, considered the first physicist, came to the conclusion that everything was made of water. Later on, Anaximander posited that air was the basic building block of all matter. Then Heraclitus argued that no, it was fire. The first atomic theory of matter dates from the year 450 BC. A philosopher, Democritus of Abdera, believed that everything was made up of very small particles, smaller than we could see or even imagine. He hypothesized that there were an infinite number of particles of all shapes and sizes. Democritus invented the word atom, a Greek term meaning indivisible. The first real connection between atoms per se and physics took place in the early 19th century. A versatile English chemist named John Dalton dared to think about weighing atoms. As strange as that seemed, it was certainly a logical line of reasoning. Atoms are material entities and therefore ought to be weighable. Dalton, of course, did not try to weigh each atom and calibrate its heft in grams, but he did manage to figure out when one atom was heavier than another. In fact, he was the first scientist to propose classifying atoms by their weight. Needless to say, Dalton probably didn't realize that he was toying with one of the primary bases of modern physics. In 1860, a young Russian chemist, Dmitry Ivanovich Mendeleev, argued that elements must be bound by some kind of uniting factor. He determined that the atoms making up different forms of matter had to be similar, and that they could be classified by their atomic weights. Mendeleev carried his ideas out. He classified the 63 chemical elements known at that time according to their various properties. And this was the result: the periodic table. Hydrogen, lithium, beryllium. Mendeleev was so confident of his hypothesis that he left empty spaces for the unknown elements that in theory would be discovered later. His theory was not accepted by many of his scientific colleagues, but as he predicted, the missing elements he knew must exist were soon discovered: gallium, scandium, and germanium. The periodic table was accurate. It constituted clear evidence that nature was structured in a specific order. Mendeleev's periodic table also suggested that atoms were not indivisible, a prevailing tenet at that time. In 1897, John Thomson, the director of the Cavendish Laboratory in Cambridge, found the first subatomic particle. He called it an electron. In 1920, Ernest Rutherford, Thomson's protege, found the proton. And in 1932, James Chadwick, a physicist on Rutherford's team, conclusively proved the existence of the neutron. Rutherford himself designed an atomic model that is the foundation for today's conclusive model: a nucleus made up of protons and neutrons and several orbiting electrons. Something very much like a minute solar system. Classical physics could not explain atomic and subatomic particle behavior. Newton based his laws on interactions involving celestial bodies. But those premises fail to apply at an atomic level. Electrons, protons, and neutrons do not behave like a falling apple or a planet in orbit. Something was amiss. And this was the reason quantum mechanics came into being. This is a complex, imaginative, and quite ingenious theory that explains the curious behavior of atomic particles. Quantum mechanics shook classical physics to the roots, and philosophical thinking in general. One of its most revolutionary postulates was the so-called uncertainty principle, put forward in 1927 by the German Nobel Prize winner Werner Karl Heisenberg. The uncertainty principle held that there existed specific quantum mechanics properties that distinguished atomic behavior from Newtonian physics. It was an intriguing idea. The simple observation of a phenomenon invariably altered the nature of the subject under observation. Heisenberg discovered that it was impossible to measure two properties of the same particle at the same time. He found that an observer might be able to determine, say, the exact location of an electron in space, or its speed, or its trajectory, what physicists call momentum. But it is not possible to determine two or more of these coordinates simultaneously. Any attempt to do so is doomed to failure. The seemingly endless discovery of new particles, however, brings into question the established atomic model. Today, we know that there are more than 200 subatomic particles. How can such complexity be ordered? Is it possible to explain electron dynamics and planetary dynamics with a single theory? Subatomic particles are obviously very small. So small, in fact, that they cannot be seen even by the most powerful microscopes. They are the tiniest objects known to man. High-energy physics relies on various different procedures to observe and manipulate subatomic particles. One of the most efficient of these involves high-speed collisions. This takes place in machines like this one, in particle accelerators. Basically, a particle accelerator is a vacuum tube surrounded by electromagnetic devices. Theoretically, it's simple enough. Imagine a proton moving through a tube at a speed of 300,000 kilometers per second. Upon impact with another kind of matter, energy is released as heat. Imagine temperatures as high as 10 billion degrees Celsius. Under such conditions, energy changes into matter, but not just any kind of matter. It's transformed into new particles with very specific properties. The precise moment of impact is recorded by the accelerator's instruments, and so we obtain precious information on the released particles, the paths they take, and their total amount of energy.
We want to know what the smallest objects are. And if we can understand the smallest objects and how their behavior is with them, then we can build up from that the more larger objects that we see and touch and smell in our world. We want to be able to have a basis of explanation for the world in which we live. And we know that we are made of complex molecules called DNA, very complex molecules. Those molecules are made of atoms, hydrogen, carbon, nitrogen, all of the important chemical elements that make these vast molecules. We then look at the elements themselves, and we look inside and we see their structure. They have a tiny nucleus and clouds of electrons around them. Those are atoms. We look at the atoms and we say, what are atoms made of? We're going down in space, down in hopefully simplicity. We look at the nucleus of these atoms. They're made of particles called neutrons and protons. And each phase, each stage of this, from molecules to atoms to nuclei, we use particle accelerators as powerful microscopes to allow us to determine the properties of these objects that are so small that it takes 1 million atoms to cover the size of the period at the end of a sentence in a newspaper article.
In the 1950s and 60s, scientists were able to work with increasingly more powerful accelerators. New particles were discovered almost daily. Muons, pions, neutrinos, sigmas. The simple pattern of matter conceived in the 1930s suddenly exploded into something much more difficult to grasp, or so it seemed. In the early 60s, American physicist Murray Gell-Mann, who would be awarded the Nobel Prize in 1969, attempted to simplify the situation. He concluded that the particles making up the nucleus of atoms were not elementary particles, but must be made up of other smaller particles. He called them quarks. No one had ever seen a quark, but there were reasons to believe that they were out there somewhere. Starting with the quark, Gell-Mann and a number of his colleagues designed what physicists know as the Standard Model for Particles and Forces, a simple yet elegant attempt to explain matter and its interactions. The Standard Model is the result of the knowledge gleaned by scientists since the age of Democritus. The Standard Model's accuracy has been verified on countless occasions in experiments at huge particle accelerators. This center is located some 50 kilometers from Chicago. One of the most powerful such instruments, the Tevatron, is housed here. We are in the Fermi State Laboratory, known as the Fermilab. It was here that Professor Leon Lederman, the Nobel Prize winner for physics in 1988, discovered the quark known as bottom, the fifth quark found since Gell-Mann predicted their existence. The discovery was a major step in corroborating the accuracy of the Standard Model.
So the total Standard Model picture of matter is 6 quarks, 6 leptons. And their social behavior is determined by forces. The forces themselves are carried by particles. There's the strong force holding quarks together, the electromagnetic force, which binds electrons to nuclei to make atoms, and there's the weak force, which creates radioactivity. So our Standard Model has these 3 forces, these 6 quarks and 6 leptons.
The tevatron has played a key role in the history of the quark. Thanks to this instrument, the quark known as top was found, and the Standard Model structure was completed. The tevatron is a circular vacuum tunnel. Its length is 6.5 kilometers. In the tevatron, hydrogen proton beams are driven by 1,020 magnetos and reach the incredible speed of 298,000 kilometers per second. In other words, in just 1 second, a particle travels the length of this circuit a total of 45,846 times. This is a rendition of the collision in which the top quark was discovered in 1995. A proton and an antiproton collided at nearly the speed of light. As a result, the top quark and its respective antiquark were released. The Standard Model is, for the time being, the best description we have of the intriguing world of subatomic particles, but it is not the end of the road. Its validity depends on somebody, someday, confirming the existence of a yet undiscovered entity in the already crowded subatomic world, the most wanted of all particles, the so-called Higgs's boson. This story begins in the 1960s. Peter Higgs, a theoretical physicist at Edinburgh University, imagined that every particle whose behavior was explained by the Standard Model must interact with this unknown particle. It was this interactive force that gave rise to the property known as mass. That's to say, the stronger the interactive force, the larger the particle mass. The proving of Higgs's theory will be a truly historical event. Science will have brought us closer to the origins of everything. The only problem is, the elusive boson remains, as yet, undiscovered. But particle hunters around the globe continue to search. In fact, many of them have set their hopes on this machine, the LHC. We are now entering the premises of the European Centre for Nuclear Research, better known as CERN. This center is, along with Fermilab, the most prestigious such project in atomic research. Once this was the home of the LEP. The LEP was an underground accelerator measuring 27 kilometers in circumference and located near the French-Swiss border. The LEP began operating in August of 1989, and there were attempts to detect the famous Higgs's boson. There were even times when it seemed as if the particle had appeared. But alas, they were just false alarms. Towards the end of the year 2000, the LEP was finally retired. The LHC will replace it. It is a marvelous machine indeed, and great things are expected of it in the 21st century. The LHC will be the most powerful particle accelerator in the world and will begin operating in 2005.
You never know what a new machine will discover. This has to be said, because that has happened in the past, that machines done for doing something, they did a completely different discovery. But certainly the LHC is supposed to explore completely the issue of the Higgs particle. And the other thing that seems within the realm of LHC is the issue of supersymmetric particles and whether they are related to the dark matter of the universe. If this is so, if the answer to the dark matter in the universe is supersymmetric particles, they should fall into the domain explored by the LHC.
Everybody hopes the coveted Higgs's boson will one day appear. But what if someone proves that this particle doesn't exist? In that case, scientists would simply have to go back to the drawing board and review each and every particle research study carried out over the last 50 years. But fortunately, it appears that the probabilities of that happening are very slim. In the meantime, scientists are busy trying to solve some other nasty conundrums posed by the Standard Model. For example, why is it that there are so many particles and forces in nature? Is this how the universe was created, or is there some other simpler explanation? Solving questions like these would actually be akin to explaining everything. It would constitute the ultimate hypothesis of the universe. It would be the theory to end all theories. The most disturbing question of all may be how to account for the four forces that govern the universe under just one common criterion, a dream also known as the unified theory of physics. Forces can also be construed as interactions, and they are nature's glue. They hold things together, all the different elementary components, be they molecules, atoms, quarks, or leptons. Gravity is the most familiar force of the four, and it's the only one that does not figure in the Standard Model. Of course, thanks to gravity, we live with our feet on the ground, and the planets revolve around the sun. But another much stronger force is that of electromagnetism. Electromagnetism is what bonds negatively charged electrons to atoms' positively charged nuclei. This force governs chemical reactions, and therefore life itself. Less visible interactions are those that occur inside the nucleus of an atom. The weak nuclear force that is the cause of radioactivity, and the strong force that bonds quarks.
Of course, gravity is obviously present on an astronomical scale because it is visible. But when we're talking about particles with very little mass, very minute mass counts, then gravity among these particles is very weak. We have to probe to be able to know in detail if the description of gravity is truly accurate. Initially, there are theories that do advance the possibility of unifying gravity with the other three already unified forces. If this were the case, we would have a unified description of all the natural forces. However, I think we still have much to do in this area, because the unified gravity theory and the other unified forces theories are theories that simply cannot be tested experimentally yet.
This might very possibly be one of the first key missions for the new LHC accelerator, although the experiments that would have to be carried out to do so would require an energy supply about 1 billion times greater than that generated by current means. Such fabulous magnitude was only generated once, a long time ago, a few million years after the Big Bang. Subatomic physics is now poised to explain in the near future realities that are only fantasies at present. We know that someday mankind will be able to travel the 75 million kilometers to the planet Mars in just 10 days. We know that, in a more or less near future, mankind will be able to reach the most distant planets in the Milky Way galaxy. The secret is antimatter, one of those favorite buzzwords used by science fiction writers. The story of antimatter began in 1928. The theory of relativity was still fairly novel, and Max Planck had just set out the bases of the quantum theory. It was then when a young British physicist, Paul Dirac, dared to make one of the boldest speculations in the history of science: the existence of an anti-world, identical to ours, but made up of antimatter. Dirac had reached a strange conclusion after trying to come up with a mathematical equation that would make quantum mechanics and the theory of relativity compatible. He came up with two different solutions, actually. One of them was applicable to negatively charged electrons, while the other was feasible if electrons were positively charged, something that nobody had ever hypothesized. Dirac inferred that, for every particle, there must be an identical antiparticle with the opposite charge. To each electron, there had to be an anti-electron. Dirac's conclusions led scientists to start looking for antiparticles. Professor Carl Anderson of Caltech reported the first significant results in 1932. In a series of experiments with cosmic rays, Anderson found a new particle similar to the electron, but positively charged. It was naturally Paul Dirac's anti-electron. Anderson called it a positron, and both scientists were awarded the Nobel Prize in Physics. In 1955, not long after one of the first large particle accelerators was turned on, a group of physicists at Berkeley University got a look at the first antiprotons. Since then, the discovery of antimatter has become a routine process.
Antimatter is basically the opposite of matter. There's a standard model. The standard model basically consists of quarks and leptons. Okay, so you've got the top quark, bottom quark, charm quark, up quark, down quark, strange quark. There's 6 of them. You've got the leptons, the electron, muon, and the tau, and you've got their associated neutrinos. Okay, and that's on one side of the chart. On the other side of the chart, you have their mirror image. Okay, and that means that if you have a proton, which is made up of up and down quarks, then an antiproton is made of anti-up and down quarks. Okay, so it's basically the opposite. It has exactly the same mass, exactly the same but opposite charge. So a proton has a charge of 1. An antiproton has a charge of -1. Okay, they have the exact same mass. They have, as far as we know, the exact same lifetime. If you had an antiproton here and you had a proton here and you let them sit, they would last the same amount of period of time. So it's basically the opposite state of matter.
Positronic androids, anti-neutrino planets that pass through the Earth, antimatter worlds, unimaginably long intergalactic travel. Antimatter has been the basis for some of the most intriguing science fiction stories. At the beginning of the 21st century, high-energy physicists are hard at work on this subject. In some aspects, their findings probably won't change much. Then again, there may soon be manned space missions to Mars with less than a gram of antimatter as the only fuel. Energy equals mass times the speed of light squared in a vacuum. E equals mc squared. The work of Albert Einstein, 1905. It's almost certainly the most widely known mathematical expression of all time. It explains, among other things, that mass is an extremely concentrated type of energy. Physicists tell us that a car engine could run non-stop for 100,000 years on the energy contained in 1 kilogram of chocolate, of apples, or just about anything else for that matter. The problem is, we don't know how to harness that energy. But we're learning. We're learning how to obtain energy from antimatter, though we still have a long way to go. A collision between matter and antimatter would theoretically produce the greatest abundance of energy imaginable. Nuclear fission, which powers atom bombs and nuclear power stations, only transforms 1/1000th of the potential energy involved. Nuclear fusion, the breathtaking process that fires the sun and hydrogen bombs, converts just 1% of its fuel. In a matter-antimatter collision, 100% of the matter involved is converted into energy. Hypothetically, the collision of 1 kilo of matter and 1 kilo of antimatter would release an amount of energy equal to that of 43 atomic bombs of the type that devastated Hiroshima. Particle accelerators all over the world are working non-stop in an attempt to generate matter-antimatter collisions. The only problem is the masses they have to work with are too small.
When you have a proton hitting an antiproton, everything, even the rest mass, can be used in turning into new energy. So the energy potential is enormous if you have enough particles. Okay? So the first of the question is that you can annihilate these two particles and completely turn into energy. The second question is how many particles do you have? Now, at Fermilab, we produce about 1 trillion antiprotons, which sounds like a huge number. The real thing is that in a gram of matter, in a single gram of matter, there's about 1 trillion particles. There's Avogadro's number, 6 times 10 to the 23rd. So you have 1 trillion particles in a gram of matter. So if we only have 1 trillion antiprotons, then basically any time in our machine, the most we've ever collected is 1/1000th of a gram. So it's a small number. They sound like big numbers because you have 1 trillion particles, but really it's a very small weight.
Particle accelerators are the only means we have available for producing antimatter. However, scientists think that when the universe began, some 15 billion years ago, the same amount of antimatter must have existed. This raises yet another of those great enigmas surrounding the standard model for particles and interactions. What happened to antimatter? Why didn't matter and antimatter destroy each other, generating a universe of pure energy with no mass whatsoever? Researching the tiniest realms of the universe has invariably given rise to countless mysteries, many of which are still unsolved. However, at the same time, as has been the case with practically all scientific research, particle physics continues to produce a growing list of practical applications. In the 20th century, we witnessed the boom of atomic energy and microelectronics. Now we are developing systems to get in direct touch with atoms themselves. We are able to observe and manipulate them at will. In a few years, millions of atom-sized machines will teem unnoticed all around us. They will be the first results of the Industrial Revolution of the 21st century, nanotechnology. This small square surface has the capacity to store information equivalent to that of some 200,000 books containing 25 million pages. If we wanted to store that information in one of our present-day computers, we would need a 15-gigabyte hard disk. But by 2005, this little stamp-sized device should do just fine. The project behind this is called Millipede, and it's being developed at IBM's research lab in Zurich. The project is based on principles similar to those used in old data storage systems using punch cards. The difference is, this time around, it's being done at the nanometric level. In the metric system, a nanometer is a billionth of a meter. Nanotechnology means working at the theoretical limits of miniaturization. Anywhere from 2 to 10 atoms fit into a nanometer. Destroying infectious microbes. Locating cancerous cells and removing them one by one. Cleaning the environment by removing dangerous residue. Creating atom-sized supercomputers. There's hardly a human endeavor that would not be improved by the application of nanotechnology. All matter is made up of atoms. Once we are able to manipulate them, the possibilities in practically every area of human activity may be limitless.
The main fields covered by nanotechnology is perhaps a little difficult to describe because nanotechnology has become so broad an endeavor, or a very broad interest. There are people working with nanoscale particles, that is particles with a dimension of the order of a nanometer or several nanometers. There are people working with nanometer-thick metal films and ceramic films. There are biologists working with bacteria, which they've learned to pattern on surfaces which have patterns on the order of several nanometers or tens of nanometers. It's really a tremendous opportunity, and so many scientists have become active in this area. And so biologists, chemists, engineers, material scientists, physicists have all had their contributions to this field. So there's many areas that people are interested in.
In 1959, Nobel Prize winner Richard Feynman predicted the advent of nanotechnology. His ideas became reality with IBM's scanning tunneling microscope in 1982. Since then, the manipulation of matter on an atomic scale has continued unabated. Technicians working in a laboratory in New York have created a 12-nanometer-long engine that in a few years will be employed in anti-cancer therapies. Scientists at the University of Basel are working on a nanometric-scaled biomechanical scanner designed to fight cancer cells from within tumors. Nanotechnological devices are manufactured in two different ways. One is known as the up-down approach. It entails the progressive reduction of dimensions. The second, called the down-up approach, uses the opposite process. Objects are built by assembling them atom by atom. Working at the nanometric level is not easy. Atoms are extremely delicate, and despite all our progress, they continue to demonstrate a peculiar form of quantum rebellion. During the assembly stage, for example, an atom may split for unexplained reasons. It may be due to a slight variation in temperature or because of some undetected interaction with an invasive molecule. In order to reduce such risks, experts have started looking at models designed by nature. Not that we can faithfully reproduce them yet with the necessary precision, but we do know that nothing can store information like a DNA molecule. No external protection mechanism can match the wall of a living cell. As far as nanorobots are concerned, nobody has designed a better locomotion system than the flagella used by supposedly primitive bacteria. Building nanostructures is no easy feat, to be sure, but it probably won't be long before atomic-sized devices will be a part of everyday life.
Nanotechnology is real today. The new part of nanoscale science will take, depending on what you're talking about, 5, 10, maybe 20 years. I could imagine molecular electronics coming into existence maybe 15, 20 years from now. And then, of course, there's the life sciences side of things, biotechnology, which is another aspect of nanotechnology that is not really something that is a main part of IBM's business, but we're very well aware of that, and we actually do have activities in biochemistry and biotechnology.
Nanobiology, nanomedicine, nanoelectronics, terms that will probably become familiar sooner than we think. And it's possible that the lines between them all may vanish. And in a not-so-far-off future, computers might be made of biological matter. They might even be able to repair themselves. Despite the thrilling and seemingly endless discoveries associated with the most minuscule part of our universe, we should remember that the 21st century has started and we still haven't found Higgs's boson. And of course, no one appears to be on the verge of announcing the key to the great unified theory of the universe, nor are we certain that there isn't something simpler than the standard model for particles and interactions. Quantum mechanics' exclusive postulates and Newton's laws are as unresolved today as they always have been, though they still seem to explain much of our world in their inimitable ways. The unusual realm of the microcosmos, it has changed our lives, and will continue to, even after the mysteries of the origin of everything have been revealed.